Hi everyone. This lesson is about the binomial probability distribution. So we'll begin with a bit of a definition here, which is in this grey box. The binomial probability distribution must consist of a fixed number of trials, and we call that number n. So that's important. Without that, these rules won't apply. Every trial is a Bernoulli trial. In other words, there are exactly two outcomes, and we've seen in our previous lessons the idea of P is the probability for success, Q is the probability of not succeeding in the trial. Each trial is independent. So this would be, for example, if we were doing an experiment where we drew, say, coloured marbles from a bag, we would have to replace the marbles after each attempt so that the probabilities remained fixed from one trial to the next. And finally, the variable that we look at is the number of successes in our trials, but the number of successes, that's it. So let's take a quick look at a few examples here. First, whether we can apply those concepts to identify which of these examples are actually binomial probability experiments. So tossing a fair coin many times and noting the number of tails. Well, tossing the coin, there's two outcomes, but it doesn't say a fixed number of trials. It just says many times. So this one is not a binomial experiment. Selecting and replacing a pen from a basket that contains 5 red and 7 black. Well, the fact that we're replacing means that there will always be the same number of red and black pens for each trial, so the chances of success and fail are fixed. It's 12 times, we're repeating, fixed number. We're recording the number of red pens. So let's say that red pen was success, black pen was fail. So yes, this is a binomial experiment. It meets all the criteria. Selecting 25 people at random from the population, so fixed number of trials, recording their age in years. Well, there are more than two outcomes there. Selecting 15 at random, fixed number of trials, noting if they have more than one sibling. So more than one sibling is success, less than one sibling is fail. Now, admittedly, different families will have different numbers of siblings. But if you chose from a very large population, then the probabilities of the different numbers of siblings would, because of the law of large numbers, approach fixed values. So yes, this is a binomial experiment, as long as that condition about the population has to be a large number in the population. Now then, let's take a look at a little bit more detail about how we apply these ideas. So here's a typical binomial experiment. We've got, we're rolling the die 3 times. Success is rolling a composite number, either a 4 or a 6. Fail would be not getting that. So a 1, a 2, a 3, or a 5. So let's start by writing down here the conditions. N equals 3, because it said rolling 3 times, n is fixed. Probability of success was getting a 4 or a 6. Well, there's 2 numbers there out of 6 outcomes. That's 1 in 3. Q, the chance of not having a successful outcome, that would be 4 in 6, or 2 on 3. So that's the fixed P and Q. That doesn't change from time to time. Now, let's think of all the different ways we could figure out how many different outcomes occur. Now, first we'd probably think of a tree diagram. So we could have, now I wouldn't be putting heads, tails, or different numbers. I'm just success and fail. So the second roll, I could success or fail, successful outcome or fail, and then the third roll. Now, you'll remember tree diagrams from earlier years at school, and you'll probably also remember that they're very annoying to draw because they rapidly get out of control in size. In fact, a tree diagram past the 3rd level is probably about the limit for what I can draw. Now let's summarise these outcomes here. This one was 3 successes. This one, success, success, and 1 fail. This one, we had a success, then we had a failure, then we had a success. This one, a success followed by 2 fails. This one was failed, and then we had 2 successes in a row, we had fail, then success, then a fail on the third try. This one was 2 fails in a row, followed by success, and this one was 3 failures in a row. Now, when we do these experiments, we really only care about the number of successes. We don't care the order in which they occur. It really is just about the number of them. So that one there, 3 successes, there's no other repetition of that. That's 3 successes. Now what about 2 successes and a fail? Now the next one is also 2 successes and a fail, even though it occurred in a different order. And then this one is 2 successful outcomes and a fail, because remember, all 3 of those are the outcome where the number of successes was 2. So they're really all the same outcome in terms of this binomial experiment. Then we had 2 fails, that one had 2 fails, that one had 2 fails, all 3 of those are the same outcome, and finally we had 3 fails, and there's only one way in which that could occur. Let's write down the probability of getting 3 successes. Now typically we might do this in some sort of a table, so we'll put down here x, and x could be, let's get 0 successes, 1 success, 2 successes, 3 successes. Then let's write down the outcomes, and then we'll write down the probability. So 0 successes, well, there's only one way that could happen. That was the 3 fails. The probability of that, well, there's one way that could occur. The chances of failure were 2 over 3. And we would multiply that 3 times. In other words, we would cube that. And that gives me 8 on 27. Now what about 1 success? 1 success are the green ones. So I could have success, fail, fail. I could have fail, success, fail. I haven't left myself enough room here. I can fix that. And we could have, let's see, the success, 2 fails, and then a success. Let's just move that across a little bit so I don't get totally stuck there. So there are 3 different ways this could occur. Each of these had 1 success. Now the chance of success was 1 in 3. So if you like, that's just to the power of 1. And there were 2 fails. The chance of a fail is 2 on 3, but because there are 2 of them, we square that. Now that's going to end up as 4 by 3, that's 12. And it'll still be, 3 3s are 9 times 3 is a denominator of 27 there. Now what about the 2 successes? Well, we could have 2 successes followed by a fail. We could have a success, then a fail, then a success. Or we could have, sorry, fail would be first this time. We could have the failure on the first go, then 2 successes. Again, there's 3 ways this could occur, 3 different possible ways this outcome. This time, for the successes, we square them because there were 2 successes, and the fail is just to the power of 1. So that's going to end up being 6 over 27. And lastly, we could get 3 successes in a row. There's one way that could occur, 1 over 3 cubed, and that's 1 over 27. Now if you check it out, the sum of all of these probabilities add up to equal 1, because they have to. It's a probability distribution, and every single probability in that table represents all the possible outcomes. So it has to add up to 1. It's not like there's anything else that could have occurred. So we had a complete tree diagram. Now there's a rule for this, and we would say that, so remember, capital X is our event. The event is the number of successes, and that could equal 0 or 1 or 2, etc. And this would equal n, the number of trials in the experiment, c, x, then our probability of success would be to the power of x, and our probability of failure would be to the power of n minus x. That's a pretty important rule. That's our formal definition, if you like, of a binomial experiment outcome. That's all these things we were calculating here. I should make note that x can range from 0 all the way up to n, the number of trials in the experiment. Let's take a look at an example here. So you can see our formula there, and here is an example of such a formula. Remember sometimes that the numbers where I've written n, c, x for a combination can be written like this as a column vector with the two numbers above each other in the brackets. So part A, how many trials in this experiment? Well, that would be the number at the top. So that would be 6. N equals 6. I got that by looking here. What is the probability of success in an experiment? Well, that would be here. Remember, we've got p to the power of x, so that would be 0.2. The probability of success, p, would be 0.2. They didn't ask for it, but I'll just make a note that therefore fail would be 0.8, and that's what they've got next. Show the distribution as a table. So what that means is I need to put a value for x and then a value for the probability that x equals x. So that's the experimental outcome. 0, 1, 2, 3, 4, 5, 6. And each one of these entries in the table will be calculated with that formula that we just talked about. Now, let's have a look at how we would enter that onto our calculator. So remember, from the options key and then to the right we have a probability menu. I could put 6, C, 0, and then I could put brackets 0.2 to the power of 0, and then I could put 0.8 to the power of 6. So that's 0 successes. And calculate, and I get an answer of, wait a minute, that shouldn't be an answer of 1. 0.8 to the power of 6 isn't 1. Something went funny there. Let's go back, and sometimes the calculator gets weird if you don't put a multiplication sign in between some of these different parts. Let's try that. That's much better. I don't know what it did the first time, but there's an important tip. Multiplication signs between these things on the calculator. So we have here 0.262 for the first one. 0.262. It was a 1, I think. Now that's going to be pretty tedious if we're going to have to go back and change this to be a 1, then this to be a 1, and then this to be a 5. So I think there's probably a better way. And there is a better way. There's a couple of different ways I could do this. Let's just chuckle that out. Firstly, I could go something like this. 0 stored in variable, where am I? X. Where are you? X, you're down here somewhere. There you are. Now I could write my formula using the pronumeral x, pretty much exactly the way the formula reads. So let's try that. I would start with 6, C, and this time I have to put it x, don't forget that multiply like I did last time, 0.2 to the power of x multiplied by 0.8 to the power of, now this is where I'd have to go 6 minus x. Fingers crossed we get the same answer. Phew. Now if I wanted to quickly calculate the next entry, I would go back and put a 1 stored in this. By pressing enter, it recalculates everything. So the next entry in my table is decimal 3932. Let's write that one down. So that's the second method that we could use on the calculator to do these things, and it's certainly better than the first, but there's still an even better way. So let me just show you. Let's pop across here to the statistics app, and here in this list I'm going to store the numbers 0 through 6, and these represent the values of x in this experiment. So we could get 0 successes, or 1 or 2 or 3, etc. Now I'm going to use F5 here for distribution. It's a binomial distribution, and it's a binomial probability distribution. Now my data is stored in a list. Sometimes that will say variable, but check to see that it's on a list. You can use F1 to do that. And it is stored in list number 1. I do need to tell it the number of trials. It's 6 trials in this experiment, and the chance of a success is 0.2. I don't need to tell it Q, it knows that. Now where do I want to save these? Well, I want to save them in a list, and I'll save them in list 2 so I don't write over the top of the numbers that are there. Now I move down to execute and I press F1 to calculate. There they are. You can see that the first one agrees and the second one agrees, but it gives you all the answers in one go. Now if I just go back to the front here, there's my list and there's my entries running down for the rest of the table. So it calculates all of them very quickly, very accurately, and then you can copy them out. Now I'm not going to waste the time of writing the rest of them down. So that's how to use the graphic calculator to do these quickly. I do have one other very short example here to do. So let's have a quick look at this one. Jeremy sits for a test containing 10 multi-choice questions. It seems like every question is a trial in an experiment, and there are 10 of them, so n equals 10. Each has 5 choices. Calculate the probability that Jeremy scores 7 correct answers after guessing each one. Well, if he guesses each one and there are 5, let's say that it's equally likely, so he has a 1 in 5 chance of guessing correctly or succeeding, and a 4 in 5 chance of failing. So we want the outcome that x equals 7. Our formula then would be 10c7. Chance of success is 1 on 5 to the power of 7. 4 on 5 to the power of 3. Now I think when you calculate that, I'll leave you to calculate that one out, you'll find that Jeremy has a very small chance of success if he was to actually hope to get 7 correct on a 10 question multi-choice, and he was just relying on pure guesswork alone. Please don't be like Jeremy. No offence to anybody who's actually named Jeremy out there. Okay, thanks for watching, and I'll see you next time.